Okay, so for this video, I'll discuss the limitation, or sorry, not limitation, but when the linear regression has its limitation, we cannot describe the data using just a line. We can provide a curve that represents this data point. We can have a higher order equation, algebraic equation, that represents this data, which is called a polynomial regression. So we can imagine instead of a straight line, we can have a parabolic curve here that might express this line. So a parabolic curve is usually an ellipse, or sorry, not ellipse, but an ellipse could be, pero the simplest quadratic second order is the parabola. Yan. So the general polynomial regression will be into this form. So this is not only limited to quadratic functions. We can also utilize this uh, third order, or sorry, not third, but third order, third degree polynomial, fourth degree, fifth degree, and so on. So we can consider only a quadratic function to solve. So we have, instead of two parameters, we have two parameters. We have an additional term, a2x squared, which represents this curvy pattern. So this will increase our flexibility in approximating the the regression, no? So the approach for this quadratic, no, regression is similar to what we did last time, and you can see a pattern here, no? So if you can imagine, this is when we have only a linear regression, right? But if we add more, as you can see, the xi will be squared toward the right, no? And then diagonals here will be the same, and then the same, no? So we have an increasing here of square, and then this will be also increasing in square, no? So that will be the pattern. And then for additional rows here, you can square, no, the xi. So therefore, if this is a cubic function, then we have xi cube yi, for example. Ayan. So remember this formula. Now, low order polynomials are usually obtained for better fit, although the problem with higher order than 4 or more, if the quadratic equation is has an order of 4 or more, then it turns to be ill-conditioned, no? What I mean by ill-conditioned, meaning it will be oscillating, and the accuracy of your prediction might not be useful, no? Since a small change, no, ibig sabihin kasi ng ill condition, the simplest definition of ill condition is for a small change there is a wild sensitivity. So the sensitivity is high, the accuracy will be compromised for higher order polynomials. So usually we can use below this fourth order, we can just use third or second. So let's consider again another set of data. So the velocity is measured at various points along the boundary layer in a free convection over a vertical plate are given below. So you can imagine you can we have, let's say, a boundary layer, and then there is a convection between the air and the plate. So you can imagine for xi is equal to 1. So this is the point. So there is a velocity here, there is a velocity here, there's a velocity here, and so on. So maybe this is at an opposite, no? At an opposite direction. Since when we increase the xi, the velocity will also increase. So usually the first portion is the highest velocity, and the velocity will decay towards the left, no? But anyways, now let's say this is the data. Let's find a second order polynomial to fit this data. So how do we do this again? So for the formula, if you can remember, we have the 3 by 3 matrix. So n summation of xi, summation of xi squared, summation of xi, summation of xi squared, summation of xi cube, diba? And then summation of xi squared, summation of xi cube, and then summation of xi to the fourth. So we will do this, and then we have a not a1 and a2. Yeah, so we have three unknowns, and then we have summation of yi, summation of xi yi, summation of xi squared, and then yi. So you need to tabulate all of this, no? So for n, how many data points? We have 5. So n is equal to 5. So okay, we're good with this. So for the summation of xi, what you should do, we should tabulate this again. I guess I should tabulate this here, no? So the total of this xi, summation of xi, that is equal to, so I have a cheat sheet here, no? To save time. So the summation of this is 15. The summation of y is, we have 152. 152.56, 152.56. So that is not 56 but 152.6. So that is the sum of all your y's here. And then we want to solve for the square of xi. So for the square of xi, so we want to just square this independently. So we have 0, 1, 4, 9, 16, and 25. So finding the sum of this, what do we have here? See, I'll just write this down here since there's no no space left, no? So xi squared, that is equal to 55. So 55 here. And then for the summation of xi cube, okay, so we're good with this. We're good with this. So for x cube, we want to now cube, no? So 0 cube is 0, 1 cube is 1, 2 cube is 8, 3 cube is 27, 4 cube is, I don't know now. I don't know now, no? So 64, and then 125. Yeah. Okay, so the summation of this, no, so summation of this xi, sorry, I don't need to put summation here. So the summation of xi cube, this is equal to 225. Okay, and then the xi to the fourth, so the last one. So for this, we want to find the fourth power of this x. So we have 0, 1, and then 16, and then times 3 again. So this is 81, 256, and 625. Okay, and then the sum of this, summation of xi to the fourth. So the sum of this, we have 979. 979, yeah. Now for the right hand side, so the summation of yi is already solved, no? So we have 152.6. So now the multiplication of xi and yi. So we have 0, and then 7.7, and so on. So this will be 7.2. Sorry guys, no? I'll just write this down since I already calculated the value. So 163.6, and then 305.5. So the total of the summation of xi and yi, this is equal to we have 585. So just double check this, guys. You want to study this. And then for the last one, we have the summation of xi squared yi. So what we can do here is just multiply this and this, no? So summation of x squared and I. So we have 0, we have 7.7, and then so 13.x times 13.6 times 4 is 54.4, and then 244.8, and then 654.4, 157, 152.7.5. So the sum of this, so for this, the sum of xi squared yi, that is equal to 2488.8. Yeah. So we already got everything, no, to solve. So we can just substitute the values. So substituting the values, we have n, which is 5. So yeah, we have to make things bigger, no? So we have 5. Is it 5? Sorry, it should be 16, no? It should be 16, sorry. So this is 16. So 16 and so 16 tuloy. 6 and then 15. 15 we have 55, 55, 55. We have xi cube. So 225, 225. And then x to the fourth, that is x to the fourth 979. Yeah. Okay. And then a naught, a1 and a2. And then for the right hand side, we have yi, so 152.6, and then 585.6 and 2488.8. So solving this using your calculator, you can have a value of a1, a naught, and a2. Okay, so mode 5, 2. So since 3 equations, 3 unknowns, and then input the values. So 6, 15, 55, 152.6, 15, 55, 225, 585.6, 55, 225, 979, and 2488.8. So the answer should be 2.4786. Yeah, 2.4786. And then 2.3593, and then the last one will be equals 1.8607. So therefore, if your function, your regression function is a naught plus a1x plus a2x squared, then therefore your second order polynomial, which is your regression function, is 2.4786 plus 3593x plus 1.8607x squared. So this will be your final answer. Okay. So you can try plotting these points, and you can see here that if this is your given data set, so you have this given data set, it will capture essentially the relationship, of your data. So although it did not perfectly match, it generally obeys the behavior of your data. So if you calculate your r squared here, it should be 0.99851. Okay, so it is that simple, and you can imagine the implications of this. So let's say you have your steam table. Now you can create a polynomial regression of your steam table. If you can try observing your data. But in reality, it is not applicable for steam tables. You can create, let's say, a relationship of your grades versus time. So as time goes by, what is your general weighted average? It might be increasing, it might be decreasing, or it might be staying the same. So, or you want to predict gas prices, so through time. So how does gas prices go through time? So usually it is increasing steadily through a linear function. So for quadratics, again, it depends on your data. If it looks like quadratic, you can use quadratic regression. Okay, so that will be it. So you can continue doing this for higher order polynomials, and again, this has a lot of implications in engineering and statistics. So let's move on to another topic. So for the last topic here, I will discuss the multiple linear regression. So imagine if you have two independent variables or more, and the you want to predict the, let's say, uh the dependent variable. So again, sige. So let's think of a scenario. Let's say there are two things that impact your grade. So your output is your grade, for example lang, and let's say your input is how much time, no? Time studying, no? How much time studied per day, no? And then maybe another influence or another independent variable that could influence your grade could be ano pa ba? Your sleep, maybe your sleep, no? So another input, your sleep, time sleep, no? Time asleep. Okay. So maybe if you have more than one independent variables, you can create a prediction model that represents your grade. So for more than one independent variables, so two or more, you can create a multiple linear regression. So instead of just a line, a curve for linear and quadratic regression, the representation of your output will be this plane. So given your first variable and second variable, so it can map a certain height that is your output. So the input here, and then you have a corresponding output here. Input, input, corresponding output here. So that will be your multiple linear regression. Yeah. Okay, so let's just do this now. How do we solve for multiple linear regression? So it has a general form of this. So depending on how many independent variables do you have, so for two equations, two equations, but two independent variables and one output, no? Then we can consider this simple multiple linear regression, no? So we have this, and to solve for this, we have a similar approach to the linear regression, although I won't do that anymore. We have a similar, as you can see now, we have a similar, although we have a similarity, although at this point, it is not the same, no? So, as you can see, it is a little bit different here now. So, at least you can see a pattern that we have a diagonal here that is squaring x1 and x2. And then this portion here is just x1 and x2. And this one is just x1 and x1. And then x2 and x2. So, you will make use of this formula for later. And then, we have still the summation of y. And then the summation of x1, the summation of x2 here. Times yi, no? I forgot to mention the y. So I guess let's just go ahead and solve a problem to understand what I'm trying to say here. So given these two independent variables, x1 and x2, find a multiple regression equation to predict the dependent y. So we have these two independent variables, and we want to be able to predict this variable y using a multiple linear regression. So how do we do this? So again, the formula that we should use is, okay, so we have n, no? And then we have the summation of x1, the summation of x1, and then here we have the summation of x 1 squared, and then here the summation of x2 squared, and then we have the summation of x2 here, the summation of x2 here, right? And then what's next? We have here the summation of x1 times x2, and then the summation of x1 and x2. And then we have three unknowns, so we have a0, a1, and a2. And then equals to, we have the summation of y, the summation of xy, and then x1y, and then we have the summation of x2y. So we want to tabulate this, you know, so that we can solve for this. So what is the n here? So we have 1, 2, 3, 4, 5, 6. We have 6 data points, so n is equal to 6. So we have this already figured out. So the summation of x here, I guess I can just write this down here. So the summation of x1, so the summation of x1 here, we have computation already. Sorry, I'll just look at this. Yeah, sorry. Yan. Mhm. Sorry guys. Wait lang. Okay. Okay. So, x1 here will be 16.5, summing this x1 variables. The summation of x2, so the summation of this will be equal to 14. And then what's next? So, okay na dito. x2, so x1 squared. So, x1 squared, we want to square this. So, we can create a tabulation here, no? So, x1 squared, this will be equal to, so 0, 4, so square of 2.5 is 6.25. Then we have 1, 16, and 49. So the sum of this, I'll just write this down here. So x1 squared, that is equal to 76.25. Yeah. And then for x2, okay, so we have this already. So x2 squared, we have the summation of x2 squared. So x2 here, x2, yeah, and then squared. So we have 0 again, and then we have 1, we have 4, 9, we have 16, sorry, 6 times 6 is 36, no? 36, and then 4. Yeah. So the summation of x2 squared, so the total of this, that is equal to 54. Yeah. Okay, so what's next? So we want to now solve for x1 times x2, so x1, x2. Okay, sorry, this should be red. So x1 times x2, we have 0 times 0, so 0. 2 times 1 is 2, and so on. So 0, 2, 5, 3, 24, and 14. So the summation of x1 and x2, that is equal to the sum of this, which is 48. Okay, so we are good with the coefficient matrix. Start